So far, we have talked about continuous distribution and continuous random variables. And from today on, we'll talk about a few continuous distributions, a few special continuous distributions. We'll start with the simplest continuous distribution, which is the uniform distribution. In fact, we have seen the uniform distribution already in our spinor example. The distribution of a spin, say x, of the fair spinor has the following probability density function. We have derived this probability density function in one of the examples before. This probability density function is flat at 1 on the 0 to 1 interval and 0 in other places. This distribution, in fact, is a uniform distribution. It is a uniform distribution with parameters 0 and 1. The word uniform in uniform distribution means the same over a range. So the density is the same over the interval given by the two parameter values. So the density is flat, it's the same over the interval, and and that's why the distribution is called a uniform distribution. And the uniform distribution with parameters 0 and 1 is also called the uniform distribution on the interval 0 to 1. And it is denoted by uniform 0, 1. A random variable x follows a uniform distribution is written in this way. X follows the uniform distribution on 0 to 1 interval. Well, uniform 0 to 1 is a particular uniform distribution. There are other uniform distributions as well. In general, a uniform distribution is written as uniform LH, uniform distribution with parameters L and H, where L and H are two numbers, and L is a smaller number than H. The density function of a uniform distribution on the interval L to H is given by this. So the density is flat at some value, let's say P, on the interval L to H, and it's 0 in other places. So if you draw that on a graph, then you first identify this lower and upper endpoints of the interval L and H. And on that interval, the density is flat at some positive value, P, and it's 0 elsewhere. So that's the probability density function of the uniform distribution on L to H. But we haven't answered the question what P should be. What is the height of the probability density function on the interval? So we can figure out what P is using the features of probability density functions for continuous random variables. One feature is that probability density function cannot be negative. So that means P cannot be negative. And the second feature is the more useful one. It says that the probability density function should integrate up to 1. So if we do an integral of the probability density function, that should give us 1. Now, what is this integral? realize that the probability density function is only non-zero on the interval L to H. So this integral is simply the integral from L to H, P dx. And that is P times H minus L. So if 1 equals P times H minus L, then P has to be the inverse of H minus L. So therefore, the probability density function of the uniform distribution on the interval L to H is given by this, with P equals the inverse of H minus L. So this is quite intuitive because if the interval is long, then the probability that the random variable, falls in any small neighborhood, any given length small neighborhood at any point should be lower, because the probability is getting more diluted on this longer interval. So when the interval length is long, the density gets diluted, gets lower. So that is the probability density function for a general uniform distribution. Using the probability density function of the uniform distribution, we can calculate uniform probabilities, the probability that X belongs to any given interval. Let's consider that problem in an example. In this example, we're playing an online war game. The war game itself assigns damages from enemy attacks using probability distributions. The players can be wounded by two kinds of weapons. There may be other kinds of weapons, but we're only just talking about the two. So by rifle or hand grenade. The players can be wounded by the weapons until their health point drops to 0. If their health point drops to 0, then they are out. They no longer survive. So they're out of the game. Now, suppose that the damage done by a rifle attack is R. It's a random variable R that is drawn from the uniform distribution on the 2 to 6 interval. And the damage done by a hand grenade attack is H, which is drawn from a uniform distribution on the interval 1 to 11. Now suppose your current health point is 5. You have 5 health points left. What is the chance of you surviving an attack by rifle? And what is the chance of surviving an attack by hand grenade? We can calculate these probabilities using the knowledge about the distribution of the damage done by rifle and damage done by hand grenade. So in the case of the rifle, the probability of surviving is the probability that the damage is less than 5. So that is this probability that the rifle damage is less than 5. And that can be obtained by this integral from infinity to 5. The probability density function of R, X dx. Well, because we know R is uniformly distributed on the interval 2 to 6, so the probability density function of R is 0 for any X below 2 and above 6, and the probability density function is 1 over the length of the interval on that interval, which is the length of the interval is 4. So therefore, that integral is equals to the integral from 2 to 5, 1 over 4. 4 is the length of the interval, 2 to 6. And that equals 3 over 4 is 75%. You have a 75% of chance, 75% chance of surviving after a rifle attack. And similarly, for a hand grenade, the probability of surviving a hand grenade attack is probability that H is less than 5, and that can be obtained in a similar way, except that we use the hand grenade damage density, probability density function for the hand grenade damage instead of that for the rifle damage. And that integral turns out to be integral from 1 to 5 because we know the density for H is 0, below 1 and above 11, and equals 1 over 11 minus 1 on the interval 1 to 11. 1 over 11 minus 1 is 1 over 10. So that gives us 5 minus 1 divided by 10, which is 40%. So the hand grenade is much more likely to kick you out of the game. For uniform distributions, we can define the traits for these distributions. We can define the expectation and the variances. For expectation, let's use the, we can calculate the traits, expectation and variances. For the expectation, let's use the expectation formula, which is the integral of x times the probability density function dx. And for a uniform distribution on the interval L to H, the integral, we only need to consider the integral range L to H because elsewhere the density is 0. And on that interval, the density is 1 over the length of the interval. So that gives us 1 over H minus L times 1/2 x squared evaluated on the two endpoints. So that equals 1 over H minus L, 1/2 H squared minus 1/2 L squared. And that turns out to be H plus L divided by 2, which, notice, is the midpoint of the interval. Midpoint of the interval on which random variable x has positive density. This is quite intuitive because all we know is that x is can be drawn anywhere from this interval with uniform probability, with the same probability. Then without any further information, the expectation should be in the middle of the interval, or the average should be in the middle of the interval. We can also calculate the variance of the random variable. Let's use the variance definition of the variance, which is integral of x minus expected value of x squared density dx. Similar to above, we can reduce this integral to integral from L to H. We can plug in the expectation squared, and the density on the interval is 1 over the length. Now let's just work through the algebra. First, we factor out this constant. So it's 1 over H minus L. And then we find the antiderivative of this square function, which should be 1/3 this quantity to the power 3. And then we evaluate this antiderivative on the two extreme points. So that gives us the following. So 1 over h minus L times 1/3 times h minus this midpoint to the power 3 minus L minus h plus L divided by 2 to the power 3. Now, if you look at this first term, h minus the midpoint, that should equal to 2h minus h minus L divided by 2, which should be h minus L divided by 2. So therefore, this first term is h minus L divided by 2 to the power 3. So that's h minus L divided by 2 to the power 3. And this is 2L minus h minus L divided by 2, which is minus h minus L divided by 2. And that, if you take that to the third power, the minus sign will come out and cancel out with this minus sign. So together they becomes a plus sign. Therefore, the second term is also h minus L divided by 2 to the power 3. And that gives us 1 over 12 h minus L to the power 2. So this is the variance of the uniform distribution on the interval L to h. As you can see, the variance increases with the length of the interval. This is intuitive because the longer the interval is, the less certain we are about the value of the random variable. And the more variable the random variable is. So therefore, that means the variance is higher. So these are the traits of a uniform random variable. Next, let's consider two simple operations on the random variable: shifting and scaling. So what are these two operations? So scaling x by a constant a positive constant a, means that changing a to a times x, means that we multiply x by the scaling factor a. Well, what is shifting? Shifting x by b means adding b to x. So you obtain the random variable x plus b after shifting x by b. And you can combine scaling and shifting. You can scale x by a and then shift the whole thing by b. What you get would be, first you scale by a scaling factor a, and then you shift it by b. Now, if x is uniform distribution on the interval L to h, what about ax plus b? Well, you can obtain the distribution of this new random variable using the CDF and then take the derivative. So it's convenient to give this random variable a name. Let's call this y, random variable y. So y equals ax plus b. So the CDF of y at a point little y is the probability that y is less than or equal to little y, which is ax plus b less than or equal to little y. And now recall that A is strictly positive. So this inequality is equivalent to probability 2 that X is less than or equal to Y minus B divided by A. And that clearly is the CDF of X evaluated at Y minus B divided by A. Now, if you want to find the PDF of Y, which is easier to work with, you can take the derivative of the CDF. And now that is the derivative of fx, y minus b divided by a dy. To take this derivative, we use the chain rule. First, take the derivative of fx, and then take the derivative of y minus b divided by a with respect to y. So the first layer gives you the PDF of x, and the second layer gives you 1 over a. So what you get should be this. And now remember what the probability density function of x is. The probability density function of x is a constant which is 1 over h minus L. And now we multiply that by 1 over a if y minus b over a is in h to L to h interval and 0 otherwise. So let's now simplify this condition a little bit more. We find that equals 1 over a times h minus L if, so y minus b belonging to this interval implies and is equivalent to y minus b belongs to AL, AH. And that is equivalent to y belonging to AL plus b and AL plus b, to AH plus b. So that condition can be equivalently written as y belongs to AL plus b, AH plus b, and 0 otherwise. As you can see, this quantity, a times h minus L, is actually the length of this interval. And that is a constant value on the whole interval. It does not depend on y. It doesn't vary with y. So y is a uniform distribution. Y follows a uniform distribution. So that means y follows a uniform distribution on the interval given by this shifted interval. As you can see, the shift applying to the endpoint of the interval is the same as the shift applying to x. So shifting and scaling a uniform random variable will give you another uniform random variable with the interval given by applying the same shifting and scaling on the original intervals. So that's that's how you obtain a new uniformly distributed random variable from an old one. Now let's consider an example of shifting and scaling. So shifting and scaling is often related to relabeling or changing the unit of some measurement. Suppose we consider this a spinner example again, and we now relabel the spinner or changing the unit of the measurement on the circle. This graph shows us the original spinner, which is labeled from 0 to 1 uniformly on the circle. And the spin on this spinner in this labeling system is called random variable X. Now suppose it's the same spinner, we simply change the labeling system. Instead of labeling from 0 to 1 uniformly on the circle, we take the spinner, the circle, as a clock, the face of a clock, and label the points from 0 to 12 evenly, uniformly on the whole interval. So the point 0 is still 0, point 25 becomes 3, and 0.5 becomes 6, and 0.75 becomes 9. So then the same spin in this new labeling system is called random variable Y. And Y is clearly 12 times X is a scaling of X. Is X scaled by 12. And because X follows the uniform distribution on the interval 0 to 1, Y should follow the uniform distribution given by the interval that's obtained by applying the interval for X, applying the same scaling on the interval for X. So it's 12 times 0 to 12 times 1, which is uniform 0 to 12. And alternatively, you could label the spinner in a third way. In this way, we call the topmost point not 0, but -6. And we call the length of the whole circle is still 12. Let the length of this whole circle be still 12, and we evenly distribute points on this circle this way. So the topmost is -6, the rightmost is -3, and the lowermost is 0, and the leftmost point is 3, and so on. Then we call the same spin Z. So this is the same spinner, but under a new labeling system. And the same spin is the random variable Z, and it's related to Y in the following way. It's Y -6. And it's also related to X in this way. It's 12X -6. So by the derivation we just had, this Z random variable should follow the uniform distribution from 12 times 0 -6 to 12 times 1 -6, which is uniform from uniform distribution on the interval -6 to 6. So I sometimes write closed interval, sometimes open interval. It does not really matter because we have a continuous distribution. Whether it's open, whether we include the endpoint of the interval or not, does not matter, because the probability that the random variable takes the value that equals each of the endpoint is 0. Continuous random variables takes any value with 0 probability. So that's all for uniform distribution. And in the next video, we'll talk about normal distributions.